let's continue the discussion, and now we'll move to correlation functions. And when I say correlation function, in fact, I mean correlation function of local operators. Let's say something like expectation values of local operators, a bunch of them, inserted at distinct points. And you can think of this object as we said at the beginning, the scaling limit of certain combination of lattice observables, and this is represented by some path integral which weights each field configuration by some measure. And this allows us to define operators whose expectation value gives indeed the correlation function. So from now on, we discuss local operators as fundamental ingredients, although you can forget about those operators and only discuss about correlation function. And as I was saying, this object is defined by a path integral, which means that which in a field and CFT is intrinsically time-oriented. So you have to remember that there's always in the background a definition of time evolution, which will make it more clear later. And according to this definition of time evolution, these objects are oriented in time. These insertions are oriented in time. And okay, so in order to understand how these correlation functions are constrained, we have to understand how these local operators transform under conformal transformation. One thing that I didn't mention before, but now it's time to actually make it clear, is that conformal transformation x mu going to x mu prime is such that you can show that when you take the Jacobian of change of coordinate, the x prime mu over the x nu, okay, this object is normally for rotation, it's just a rotation, okay? So something like, I would call it lambda mu nu. This is a general rotation. But for a conformal transformation, you can show that the most general conformal transformation is indeed a rotation times a factor, a scaling factor, omega of x, which is x dependent generically. It's constant only for scale transformation, but for special conformal transformation, it depends on x. And this object here is the one that actually rescales the metric, because rotation leaves the metric unchanged. So if you make a rotation, the distances remain the same. This factor omega is the one responsible for rescaling of the metric, of the matrix, and therefore dilatation and local dilatation, although angles are preserved. Okay, so under such transformation, let's ask ourselves how a local operator transforms. And to make it intuitively, we can understand that it's going to be a combination of transformation law under rotation and rescaling under some factor. Particular under rotation, an operator O, which has scaling dimension delta, and lives in some irreducible representation R, okay, and has some collective indices I, and depend on X. This object will transform, as we know, with the appropriate representative matrix, the representative of the transformation lambda, which has the same indices of the operator, collectively called I and J. And this is contracted with J, index J, delta R. And then, of course, also the X, the argument of the operator, gets transformed with the inverse transformation. And this is well known as what we have in quantum field theory. Okay, they have the same in Minkowski signature, except that now rotations are replaced by Lorentz transformation. Now, similarly, under scale transformation, you can intuitively understand that when you have scaling invariant, a good quantum number is indeed the dimension of an operator, okay? That, for instance, dimension in energy. So under scale transformation, an operator O with the mean dimension delta will rescale. So if I make a transformation lambda, this object will pick up a constant factor. So I rescale the distances, I rescale my meter. So energies will become, so if I increase distances, energy will become smaller, and so on and so forth. So O will pick up a factor minus delta operator, which multiplies the operator. And also I have to rescale again the coordinates. Again, there is a factor lambda minus 1 because energy and length rescales in the opposite way. So combining these two, okay, you can imagine that the general transformation for a conformal transform under conformal symmetry will be a phase, a prefactor, which eventually will be x dependent, and the rotation. Indeed, you can prove this. You can prove that operators, and then I'll make a comment about which operator obey to this law of transformation. And anyway, operators OI with which transform in the representation R and have scaling dimension delta under x going to x prime will transform, in fact, as a combination of the previous two transformation laws. So there will be a prefactor, which now is omega, the x-dependent dilatation, to the power minus delta. There will be the rotation, which is the same. Delta R, and then there will, if x prime is some g of x, you have to evaluate this operator in g to the minus 1 of x. So this is the transformation law of operators, but which operators? Not all of them transform in this way. This transformation law is for so-called primary operators, which, if you're familiar with the state operator correspondence, are the operators that, when acting on the vacuum, create a primary state. So concretely, this is for operators that satisfy a similar condition as primary state, but translated on operators. So in this case, since these are operators, you have to take commutators. So the condition is that the commutator of the operator evaluated in 0 is actually 0. So these are primary operators, suppose. And this condition arises when you try to implement irreducible representations of the conformal algebra on the operators. Again, as before, we have the labels of the operators that are the scaling dimension and the irreducible representation. And on top of this, you have to specify a condition on the action of the special conformal transformation generator, which is K. And we say that a primary operator is one such that this condition is obeyed. And as we will see, these primary operators are those that generate primary state. So before going there, let's stick for a second to correlation function of object that transforms in this way. And I repeat, these transformation laws are only for primary operators, not for descendant. But transformation law for the descendant can be obtained by this by simply taking the commutator with the appropriate generator. So the first thing that I would like to do in somewhat detail is an example of the correlation function of two scalars, phi 1 and phi 2, with dimension delta 1, delta 2. They are scalars, so they do not transform under rotation. which means that this transformation laws simplify quite a bit. And we would like to show that this object, up to a normalization factor that can be reabsorbed in the fields, is completely fixed. So we'll take the correlation function of these two objects, and I will call this object f of x1 and x2, which in principle, if I was completely agnostic, could depend on both coordinates in arbitrary way. Then, of course, this is not the case, because translations implies that invariance under translation implies that this f is only a function of the difference. Rotation, invariance under rotation implies that this function is only a function of the norm, the modulus of this vector, which I will call actually x12. And from now on, xij will be the difference xi minus xj. If I put the index mu, I really mean the vector. If I don't put the index, this means the modulus, the norm. So, square root of the modulus square. Okay. Okay. So far nothing new. This is the same story in quantum field theory. But now let's add the ingredients of conformal field theory, dilatation. Dilatation implies that this function f has to be an homogeneous function of the quantity x12 with appropriate degree. In particular, dilatation implies that, if you work it out, lambda of the field, I get this prefactor, then I get the same function as before, evaluated now in x12 divided by lambda. And this has to be equal to f of x12, which forces the function of x12 to be, in fact, a constant function, a constant value divided by x12 to the power delta 1 plus delta 2. As a, okay, you can make this a little more formal, but this is there's only this solution. But still, so this is what would be the case. This would be the case in a simply scale invariant theory. But in a theory which is fully conformal invariant, you have an additional transformation, which is super conformal. Special conformal transformation. And under this condition, you can show that, of course, it's not going to modify further the generic form, but super conformal transformation tells us that the correlation function of these two objects not only has a fixed form, but is either 0 or, if delta 1 is not equal, then delta 2, or if they're equal, okay, it has the form that we wrote before. In particular, if they're equal, we can rescale the field to reabsorb this C. So we just write 1 over x12 to the power 2 delta 1, let's say. If delta 1 is equal to that. So special conformal transformation restrict the form of the correlation function of two objects to be 0 if these two operators do not have the same scaling dimension. So in particular, you can imagine to diagonalize the space of operator with the same dimension and assume that you can assume that an operator has non-zero correlation function only with itself. So from now on, and this is this is always possible in a unitary theory. It's not possible, for instance, in a log CFT, but this will not appear in our discussion. So we will assume from now on that the correlation function of two scalars, in this case, phi1, phi2, is proportional to the delta in the space of operators, not only in the space of dimension. So I imagine to I diagonalize the space of operators with the same dimension. So in conclusion, we obtain a very simple form of the correlation function of two scalars. And similarly, you can show that correlation function of three scalars are also fixed, but this time the overall prefactor cannot be absorbed in the normalization of the operators because you already rescaled them in order to fix the two-point function. And so in this case, the overall prefactor is going to be physical, and we call it lambda, right? And depends, of course, on the triplet of fields that we chose. But the coordinate dependence, the space-time dependence on x1, x2, x3 is again fixed by a simple function that I'm going to write. It's x12 to some power, which is called h123, and I will write in a second what it is. x23, h231, x1, which one is missing? x13, h132, where h, I, j, k is simply a linear combination of the dimensions, delta I plus delta j minus delta k. So again, notice that the coordinate dependence is completely fixed by conformal symmetry, and the reasoning goes very similar to the previous one. You have to work a little bit harder when you impose special conformal transformation, covariance. But this time there is this quantity here. This is a three-point function coefficient, which is meaningful. It's not a normalization that you can reabsorb. And what we found is very similar to what you actually find in two dimensions. Okay, just to recall you, in 2D, two-point function of operators with depends on z and z bar, and let's say omega, omega bar. There again is again fixed. Okay. And it depends on z and omega in a very simple way. So it's z minus omega to the power h, and z bar minus omega bar to the power h bar. And again, there is a delta in h1, h2, and a delta in h1 bar, h2 bar. So in two dimension, it's very simple because the reason is the rotation group is just a single generator, it's an abelian group. So there are no indices around, especially when you work in this complex notation. In high dimension, there is the complication of dealing with indices. So we have seen the form of two-point function and three-point function of scalars. When you go to object with indices, things get technically more involved, but at the end of the day, the logic is the same. So for instance, if you were to look at the correlation function of the stress tensor, which is an object we all love, in dimension larger than 2, this will look slightly more complicated. But again, it's fixed. And notice that you cannot rescale the stress tensor. Well, you can rescale it, but there is a convenient choice of normalization, which is the one that satisfies the word identities. So let's keep it. Let's keep that normalization and do not rescale the stress tensor in order to have a simple two-point function. Then in that case, the normalization of the two-point function is meaningful. Okay, and we call it CT, is the central charge. In analog to the two-dimension. Notice that in dimension larger than 2, this is the only place where the central charge appears. Okay, it does not appear in an algebra. Okay, or, it appears also in other places. You can define, for instance, as an anomaly. But if you look at it, does not appear. You cannot spot the central charge by looking at the algebra. You have to look at correlation function. And then normally there is also a volume of the sphere SD. Then of course there is the dependence on the scaling, the dependence on coordinate to reproduce the scaling x12 to the dimension, twice the dimension of the stress tensor, which in any dimension is d. And then there is an object which reproduces the tensor structure. And I'll just write it to show you that you can do this kind of things. It's not very complicated. It's just a combination of tensors that are completely fixed, and they have to be symmetrized, and you have to subtract traces. And this object here, of which depends on x12 also, is simply the metric minus twice x12 mu x12 nu divided by x12 modulo square. Okay, this object is called the inversion tensor. And if you were to consider correlation function of objects with more indices, you would just see more tensors of this kind. You would just repeat the tensor I many times in order to reproduce the tensor structure. So just have products of this I symmetrized and traces subtracted. So notice again, the important point is that correlation function of two-point functions are also fixed for any representation R. And similarly, three-point function. Yes?
Just to point out one typo, like in the trace part of this two-point function, there will be 2 upon D. In the tensor structure part of the two-point
tensor structure, mu rho, mu sigma. What's the wrong part? Sorry.
Will it be 2 upon D in G mu nu 0 sigma?
Yes. Oh, thank you very much. Yes. Yeah, I forgot about this. Thank you. Yes. Good. And similarly, as I was saying, also three-point functions are fixed up to a certain number of constants. Okay, as before, there was an overall constant. If you start putting indices, then you might have more than one tensor structure that reproduces the same indices, which means that you would have more than one constant appearing. But nevertheless, the number of constants will always be finite. So generically, if you have operator O1 with index I, operator O2 with index J, operator O3 with index K, okay, this quantity here will be, well, there will be a prefactor, 1 over the same as before, x12 to some power, x23 to some power. Power are always the same. H1, 2, 3.
Yeah, sorry, one
Yes.
other question. Yeah, I'm still variable, by the way. So you wanted to use field normalizations, operator normalizations to get rid of the prefactors in two-point functions.
Yes.
But here you don't want to do that with the stress energy tensor. So
Correct.
how do you fix its normalization?
Yeah, the normalization of the stress tensor is fixed in terms of its three-point function, if you want. So you want to obey the worded entities, which tell you that the insertion of the stress tensor in a given correlation function, it's determined by the transformation properties of these fields. Okay, the usual worded entities. So these are, if you want, they're derived by a path integral, which assumes a certain definition of the stress tensor. So we just stick to that. So you have to impose. For now, I'll make a concrete example. So you have to choose a normalization of the stress tensor such that the worded entities are verified. And then once that is given, the two-point function now it cannot be rescaled, and it has some normalization that is meaningful. Okay.
Yeah. Okay. Thank you.
You're welcome. So generically, I was saying you will have something like H1, 3, 2, H2, 3. Okay, and then you have a sum over over A, going from 1 to a certain number, and 3, which is the number of irreducible representation that appears in this tensor product, which are singlet. So the number of singlet representation that appears in this tensor product. And each one of these tensor structure will have its own three-point function coefficient, which are labeled by lambda O1, O2, O3 with an index A. And then there will be a tensor structure which reproduces the indices, which depends on the coordinates, of course, and the index A. So generically, this is very complicated. And N3, as I was saying, is fixed by SOD representation theory. You can work it out. For our case, we'll always consider the case in which O1 and O2 are scalars. And in this case, the only operator that can have a non-vanishing three-point function with two scalars is the famous spin-L representation. So we will focus on this case. And in this case, N3 is just 1. So we will go back to the simple case that we saw for scalars. There's just one tensor structure you can write. And for instance, okay, let's make a concrete example that will also address the question that was asked before. If I have an operator phi1 in x1, phi2 in x2, and then the stress tensor, okay, you might wonder how this three-point function look like. So in this case, there will be a single coefficient, lambda phi1, phi2, and then t, let's call it. I'll just copy the formula and then I'll specify. Then there is the usual denominator. I'm not going to rewrite it. And then this tensor structure, in this case, is particularly simple. It's just a product of vectors, z1, 2, 3, nu, z1, 2, 3, nu, minus trace, where the ijk is simply xik nu over xik modulus minus xjk mu divided by xjk. And as I was saying, the normalization of the tensor structure is such that the word identities are satisfied. And if the word identities are satisfied, it means that this 3-point function here is related to the 2-point function where there is no stress tensor insertion, phi 1, phi 2, which we saw it has to be diagonal, so it's delta phi 1, phi 2. So it must be that this, first of all, it must be that this OP coefficient is 0, which is the case. And not only using the word identity, you can fix the value of lambda. So in particular, one can show that delta phi 1, phi 2 t is, okay, there is a delta. We can take it in the space of operators. And then there is a prefactor which is fixed, is minus d delta phi divided by d minus 1 volume of the sphere. So in this case, for the stress tensor only, the 3-point function coefficient is fixed, and the 2-point function instead is meaningful. For all the other operators, usually we take the opposite convention. 2-point function are normalized to 1, and the 3-point function becomes a meaningful quantity. Now, but the important point of this discussion.
Sorry, a quick question.
Yes.
Because in 2D there is the central charge, if I'm not wrong. It will be 2 delta over C. So the central charge does not appear here.
No, the central, well, depends. Again, if you rescale T such that the 2-point function of T is 1, then the central charge would appear here, square root of.
Okay, okay.
But
Thanks.
if you don't do that, the central charge does not appear. So
Okay.
I prefer to use this conversion.
Okay.
The important part is that you pick one and you stick to it.
Thanks.
You're welcome. Great. So the important point is to remember that for any choice of 3-point function, for any triplet of operators, the 3-point function is completely fixed up to a certain number of constants. And all this tensor structure, well, many tensor structure for many cases have been classified. Of course, in principle, can be done for every triplet of representation, it just becomes complicated. The more complicated is the representation. All right. The final comment that I would like to make is once you start going to higher point correlation functions, conformal covariance and the conformal transformation is not enough to fix the form of the correlation function. So for instance, 4-point function of scalars, which will play a fundamental role in our discussion. And let's take them identical, or at least to have with all the same dimension. So phi of x1, phi of x4. Okay. Certainly, it will have a factor which reproduces the properties under conformal transformation, and this factor can be simply written as x12 to the 2 delta phi, x34 to the 2 delta phi. So this factor alone reproduces the covariant properties of the correlation function. So this object has the same scaling properties. Okay, it's an invariant under rotation because we have scalars, and transforms in the right way under conformal transformation. So one might say, okay, then that must be it. Well, the problem is now with 4 points, you can start constructing invariants, and in particular, there are 2 of them. So you can show that one choice of the 4 coordinates. First of all, you need at least 4 points, and they all must appear. in the combination, in the definition of this object. And one possible object, one possible combination, which is the usual, the most used in the literature, is the following: x12 square, x34 square divided by x13 square, x24 square. You see it's invariant under translation, rotation, and dilatation. But this would be the case for any homogeneous function of the modulus of the differences. But you need really all the 4 points in order to have invariance under special conformal transformation. And an independent one is the following combination: x14, x23 square divided by x, the same denominator. These two objects are invariant under conformal transformation, which means that I can multiply the prefactor I had by a generic function of these two quantities and still maintain the right transformation. So covariance under conformal transformation alone does not allow of 4 or more objects. A small comment about notation, which will be useful later. Sometimes instead of UMV, we will use this combination. U, we will write it as ZZ bar, and V, we will write it as 1 minus Z, 1 minus Z bar. And in Euclidean CFT, these objects are indeed complex conjugate. So Z bar is actually Z star. But we will often consider them as complex independent, okay? And deal with one at a time in the complex plane. And instead, in Minkowski signature, they would be real and independent. But again, you could complexify them and think about them as complex and independent. And there is also an alternative definition that people sometimes use, and perhaps we will use it. Which is the sort of radial variable, and it's defined in terms of Z by the following expression: 1 plus rho square, and similarly for rho bar, and rho is some a radius times the phase. To give you an idea of the meaning of these sets of variables, sets of conformal invariant, you can think about them as putting using the freedom that you have to put the 4 points in special configuration. Okay, so by translation, you can always put one in the origin. By rotating, you can put one on a given line. Okay, using dilatation, you can along this line you can put one in special point. And then by using special conformal transformation, for instance, you can send one to infinity. Okay, if you remember to dimension special conformal transformation where 1 over Z minus Z0, you can just put 1 to infinity. Similarly, you can do in high dimension. And so by combining this transformation, for instance, you can always reduce yourself to a configuration where x1 is in 0, x3 is in 1, x4 you sent it to infinity along this direction, and then at this point you almost have used all your invariants. The only invariance left is rotation around this axis. You can use it to put the 4th point on a plane, and this is going to be the Z plane. And Z is just the position of x2 in this plane. Okay, so the meaning of Z is once you have used your conformal transformation to put 1 in 0, 1 in 1, and 1 in infinity, the fourth has the meaning of Z. Instead, this rho is another special configuration, which is also called conformal frame, and corresponds to put your 4 points in a special configuration that looks like this. Okay. So you put 1 point in 1. This is x4. Sorry, x3 usually it's called. 1 point is -1, is x4. And then the other two, you can put them diagonally opposite on a circle of radius r, and with making an angle theta with the horizontal axis. And in this configuration, these r and theta are the one that define rho. Okay, these two are called conformal frames, and they are useful for various things. One thing that you should remember, which is very important, is that in any dimension, there are only exactly 2 conformal invariants that you can make with 4 points. So this discussion goes across dimension unchanged. But this is important. So this the fact that the 4-point function of scalars is parameterized by a function of 2 variables is true in any dimension. Okay. Now, if there are questions, of course, interrupt me. Otherwise, I will flash another ingredient that we need in order to make progresses, because so far we only have used invariance or covariance under conformal transformation of correlation function. But as you saw, we stopped once we hit the 4-point correlation function of 4 or more points. So in order to make progresses, we need to start using the peculiarities of the quantum field theory and path integral. In particular, we have to use the fact that there exists a space of states which are related to these operators. We need to introduce a notion of time direction, evolution. We also have to use properties of scalar products and conjugation. So this is well known in 2 dimensions, so I will try just to recall the story and then proceed by analogy. And this is the concept of radial quantization, of course. So we'll probably just introduce, make a small review and then leave the consequences to the next lecture. How much time do I still have? I didn't check when I started.
You started more or less on time, so.
Okay, so 10 minutes-ish.
Yeah, well.
Okay, good. So the first observation that I would like to make is that normally in quantum field theory, we're used to foliate the space with slices, okay? And this defines the direction of the slices, or the operator that allows you to pass from one slice to the next is the evolution operator, and defines the direction of time. Now, in this case, the usual foliation by flat surfaces, it's not very convenient for various reasons. First of all, because flat slices are not invariant under rotation around the origin. Okay, so if you would like to have a space of states, or if you want define initial condition on an object which is invariant, for instance, under rotation, because you're using notation to parameterize rotation to parameterize your irreducible representation. And similarly, you would like to have an evolution operator that do not mix the concept of primary operators with descendant, which would be the case, for instance, if you use the usual Hamiltonian as P0 along some direction. So for this reason, it's better to foliate your space not with slices of constant with constant value of a coordinate x or t, but it's better to use concentric spheres, or into dimension concentric circles. So, and this is indeed the concept of radial quantization. So we will foliate our space with concentric spheres. Okay? This should be concentric anyway. And then define the evolution operator as the operator that allows you to pass from one to the next, which is simply rescaling. Okay? You pass from a sphere to a concentric one by dilatation or with positive or neg or sorry, with constant smaller or larger than one. So this is the radial direction, of course, and the operator that allows you to pass from one to the next is just the dilatation operator. And there is a nice interpretation of this object, which is by rescaling, well, sorry, by redefining or introducing, if you want, a variable tau, which is the log of the radial direction r, the distance of the sphere, the radius of the sphere, which basically map this picture to a cylinder. Okay, this is a famous cylinder interpretation. And in this picture, tau is vertical direction. So it looks more familiar to what we are used to, except that the only difference is now that is that now the space, which is in this case is just a circle, but generically is a sphere of dimension d-1, is compact. You don't have, so this is very similar to a quantum field theory on a compact space. You don't have infinite space, you just have a compact space of sphere of radius 1, but then you have the usual time, flat time, vertical direction. And so in this case, in this picture, the dilatation operator assumes the role of the Hamiltonian, the usual time dilatation, time evolution along the cylinder. So we can say, in a sense, that conformal field theory, Euclidean conformal field theory, behaves as an ordinary Euclidean quantum field theory defined on a cylinder, which is r times a sphere of dimension d-1. And
a question?
Yes.
Hi, I'm Benoit Estienne. I have a question. So if you map it to the cylinder, you don't have the proper metric to use that interpretation you just mentioned.
That's right. There is a different matrix on the cylinder, which is conformally equivalent to the flat matrix that we had in our original space.
So you have to assume that your theory behaves well under conformal change of metric. You didn't mention that so far. So just.
That's right. That's right. So when you pass from one to the other, you have to be careful, because if you have, for instance, so passing from one to the other is a Weyl transformation, okay? Because these two matrices are conformally equivalent. So generically, you can, if you didn't have any anomaly, okay, you can just compute correlation function on one side and translate them on the other side. Generically, there is an anomaly, which is the center, and then you have to take this into account. So you have to transform properly your operators. For instance, the stress tensor on the cylinder will have a one-point function, which is the Ising energy. And so on. But you can, so at this stage, it will just be a picture that will be in the back of our mind, from which we can draw a lot of conclusions. But you can make it very precise and really write a dictionary between these two, but you have to be careful.
Okay, thanks.
You're welcome. So the reason why I brought it up is because it's more familiar to think about a usual theory with the ordinary time evolution. And in particular, in that case, it's easy to understand familiar concepts. And in fact, I will import various concepts from the cylinder to the radial quantization. But I will never work explicitly on the cylinder. In fact, what will I import? On the cylinder, you have an Euclidean quantum field theory, so correlation function must be time ordered. Correlation function. This translates into having radially ordered correlation function. Sorry, probably should have been in the other way around. Let me just bring this on the other side. Okay. So that each sentence is below the right picture. Okay, so I will import in this direction. So the correlation function that makes sense in conformal field, in Euclidean conformal field theory are radially ordered correlation functions. So this you have to keep in mind. Second, at each slice in your on your cylinder, at each constant time slice, you basically have a Hilbert space of states. Okay, we know that each time we can. These basically are initial condition. These are related to initial condition, and the states defined on a given slice are those created by insertion of operators at smaller times. So at each slice, okay, sorry, the cylinder is not filled. We have Hilbert space, or a space of states if you don't have positive norm. And the state created on a given slice are the state created by operator inserted at lower times. So states tau, which means that in the conformal field theory picture, we have states defined on spheres. And how are defined these states? They are defined by inserting operator at lower radiuses. So inside is created by insertion of operators inside. Sorry, I wrote really badly. Operator inside the sphere. In particular, for instance, normally we can push on the cylinder, we can push the operator to infinite negative time. Here we can push the operator to the origin. The last, and then I'll stop, ingredient that we need is the concept of conjugation. On the cylinder, on a general ground, we have we can define states or operator phi, and we also have for each state we have the conjugate state phi, which is nothing else than what you obtain by the usual conjugation, which in Euclidean quantum field theory corresponds to so if this one is created by an operator inserted at a given time acting on the vacuum, this one is created by the operator inserted at minus the time. So the way to understand this is to write the operator as the operator in 0 times evolution operator acting on it, and then you take the usual conjugation and you flip the order of the operators, but since there is no complex exponent, you don't flip the sign of the exponent, and so the time changes. So this is a standard way of defining conjugation in Euclidean quantum field theory, and this gives us a way to define conjugation in our radial quantized conformal field theory. In particular, sorry, we get a way to define states. So if you have a state, let's say, obtained by acting on the vacuum with an operator O, we can define the conjugate one by inserting the operator at the reflected, because sending tau in minus tau corresponds to inverting the position of the operator with respect to the unit sphere. So this object is going to be 0, and then, oh, let's call it inverted. So I will tell you tomorrow what inverted means. So by importing this concept from the radial quantization, from the cylinder picture, we will be able to make progresses. In particular, we explore two consequences tomorrow. One is the existence of an operator product expansion, which is a consequence of having a Hilbert state of a Hilbert space of state on the sphere, which allows you to decompose each state into a basis, and then go back to the operator analog. And in addition, having defined precisely what conjugated states are, we can now address the question of what does it mean to have positive norm states. Okay. All right. Since I'm running out of time, I'll stop here, but I'll stay around for questions.
Okay, thanks, Alessandro, for the second lecture. And hope there are some questions.
Well, I have one question. Yeah. Like in statistical model, in two-dimensional statistical model, there are many ways to measure the central charge, like with finite size scaling, universal finite size scaling terms. How you extract? There is a way to extract this coefficient CT in a three-dimensional statistical model?
Right. Well, that becomes hard in the sense that if you're able to measure the three-point function, that would give you once you have well, I mean, you have to first of all be sure of normalizations, which means you have to properly define two-point function of scalars and the stress tensor, and then you can and then you have to measure the three-point function, which is not a very easy task. People have started measuring three-point function with Monte Carlo, but it's very very imprecise so far. Alternatively, you could try to put this object on this model on a more complicated space-time and try to see if you can measure things there, because then the central charge could appear as an anomaly. But that's probably even more complicated. Alternatively, you could measure a four-point function of scalars and then extract the leading coefficients, the leading decomposition in conformal blocks. But there are other ways. For instance, there are certain models that can exist also at finite temperature, and then in that case, there are certain observables that depend on the central charge, and then you can measure them. For instance, the O2 model, if you look at the quantum Monte Carlo, sorry, the quantum critical point at finite temperature, then the conductivity depends on the central charge, and you can hope. But I mean, the precision of these measurements is very poor because they are complicated quantities.
Okay.
If I can add, I think the challenge is to define a canonically normalized stress tensor, which would, if we had that, then we could define central charge by measuring just the 2-point function.
Right.
But it's not easy in general. Yeah.
Yeah, so I think this challenge in higher dimensions, it can be addressed by working with the slab geometry. And I think it's a similar challenge that people, for example, in lattice QCD have to also address when they do finite temperature lattice QCD measurements and so on. So,
and it depends only on one parameter, or there are more parameters in?
It's the stress tensor is the lowest dimension spin 2 object. So I think it's going to depend just on one parameter that you just have to set the normalization. So I think it could be done in a lattice simulation, but I'm not sure if it has been done. Also, another thing is to try to take advantage of the while invariance and, for example, make measurements in a half space as opposed to sphere geometry, and take advantage that this to finite, that this to a ball can be mapped to a half space. So I think using such tricks, maybe you can also do something, but there's not much. There hasn't been any. For example, we know the central charge of the three-dimensional Ising model very well with many digits, but it has not been measured on the lattice as far as I know.
Okay.
It's not very different from the free theory central charge, actually, unlike in 2D where it's very different, where it's 1/2 of the free boson. In 3 dimensions, it's not so different from the boson. It's
So,
like point.
I mean, like naively, if you take the three-dimensional Ising model in a finite geometry, and you measure the how it scales the free energy, so you get something that contains the central charge.
No. It's not, because to get something that controls the central charge, you would have to measure free energy on the sphere. And because then and also it's not going to work in 3D, because in 3D there is no while anomaly, but it could work in some 4-dimensional CFT. So it's not that easy.
Okay, thanks.
I don't know. Can you hear me?
Yeah.
Yes.
Okay, so I'm Jesper Jacobsen. So in 2 dimensions, the fantastic result comes from just considering the 1-point function of t and transforming it from the plane to the cylinder. So what goes wrong in 3 dimensions? What is the obstacle? So if you just want to consider the 1-point function, surely the 1-point function is 0 on.
You have only global transformation.
Right. You can only use global transformations, and okay, on one side it's 0, on the other side it's probably some Casimir energy, but
there's no Casimir energy in 3D CFT. It's
all right. Okay.
Because there's no while anomaly.
Oh, okay, but in 4D there would be. But besides that, I'm not sure what other conclusion you can. I mean, there's no the whole power of Virasoro, so you're lacking all this.
Okay, maybe we should have some small work group on things like this, because it's something that would be potentially quite interesting if one could measure these properties using numerical simulations or something.
Yeah, why not? It's a good idea.
Sorry, I have a question. I'm Jacopo Vichi. So why is so crucial the central charge in dimension larger than 2? I mean, it's just at the end some sort of coefficient which appears in the two-point function of the stress energy tensor, but it has not any algebraic meaning. So
Right.
physically, what it is then?
So physically, there is, well, for instance, if you compute the central charge in free theory, it's proportional to the number of fields that you have. So there is this idea that the central charge, in a sense, measures the number of degrees of freedom, which in dimension higher than 2 is not precise, because there is no analog of the theorem that, well, not for a central charge at least, is the object does not decrease in along the Archie flow. But nevertheless, it gives you a measure of the degrees of how complicated is your theory and how many degrees of freedom has. So there is this intuitive picture. And so, and also in certain theories, it can be computed exactly. So if you have supersymmetry, it's related to various anomalies, and so it's an interesting object to compute, and it's worth studying it. And of course, it's related to an universal object, which is the stress tensor. So, which is something that you have in any local theory. So it's important to understand its properties, I would say. I'm sure if there is any deeper meaning besides this.
Okay.
But one can also give a more pragmatic answer to the one that Alessandro gave. So in this bootstrap philosophy, you know, we are just trying to like make a list of all constraints that we know of, and one of the constraints that we have at our disposal is that if you take a general operator of the theory and you consider how it couples to other operators, then it will just there's not going to be any particular pattern apart from maybe some global symmetry, selection rules, and so on. But the stress tensor is very special. So we know that if it couples to one field of dimension phi with one strength, and now you take another field of a different dimension, delta prime, you know exactly. So if you know how it couples to one pair of fields, you know exactly the strength with which it couples to another pair of fields. And so, and the central charge is just a kind of a rescaling coefficient. In this point of view, it appears as a rescaling coefficient, the proportionality factor, which is an overall thing.
Mm-hmm.
So, but you know, so the really important thing in practice for the bootstrap calculations is going to be this universality in how the stress tensor couples to everything. And central charge just parameterizes this universality. But it's also true that, you know, we always like we tiptoe about around the central charge, and you know we hope that one day maybe there's going to be some deeper meaning discovered of the central charge even in high dimensional CFTs, which has not been done so far. You know, that's kind of our hope.
Okay, thank you.
Any other questions?
Hey, Wiese, can you make us a small table of the two-dimensional Ising model and the most important operators and how you would label them in 3 dimensions? How you call these objects?
Sure. We'll discuss this tomorrow.
Okay.
Make it precise.
And I postpone my question.
Yeah. Yeah. The idea of tomorrow is to work through the application of all these concepts in a concrete model, and I chose the Ising model indeed.
Alessandro, can you see questions on chat? There's a question from Changu.
Okay, very good. In 2D, 1 plus 1, the same transform to cylinder. I'm not sure I understand the question.
Well, I think the question is that that there is this interesting. There are two different reasons to consider the cylinder geometry in 2D.
Right. All right. There's the duality.
I think you would have to read the whole question aloud because
Not
others
everyone
can't
sees it.
see.
Okay, let me read the question. So
Okay.
so Xangu Kao is asking in 2D. The same transform to cylinder relates quantum field theories at t equals 0 and t larger than 0, thermal field theories. Does analog exist in higher dimensions?
I mean, in high dimension, you can talk about thermal field theories, of course, and there's always this idea of compactifying the time. Okay, but the problem is there is no you cannot pass from the cylinder. There is no duality, ST duality. So I mean, you can definitely compactify time, and then you would end up with a geometry which is not a cylinder. So I'm not sure if that.
May I add a comment on this, please? Do you hear me?
Yes.
Yeah. I mean, the question is exactly about the cylinder, because there is although there is no conformal transformation, Jesper was already mentioning that, there is nevertheless an empirical remark on a certain analogy. Because the cylinder geometry, when we are in 2 dimensions, that has a feature that the decay of the correlation function, the correlation length which you find on the finite geometry, is that this correlation length is proportional to the corresponding scaling dimension. That's a very standard result in 2D. However, if you go to 3D, of course, you can define cylinder geometries, and you could look at the critical point. Are the correlation lengths, again, proportional at least, to the corresponding scaling dimension? And there is a couple of models in 3 dimensions where indeed that seems to be so, but in the 2 finite directions, you must take anti-periodic boundary conditions. That analogy exists, but as a purely numerical remark without any understanding whatsoever.
Okay, so I should say that people do not usually play these games on the cylinder because it's just it's just very complicated to work on the cylinder. So sincerely I don't know many work trying to compute these things on the cylinder. Of course, you can compute a 2-point function on the cylinder, and this will be given by a sum of how does it go? It's exponential of it's a sum of discrete of a discrete spectrum. So the spectrum is discretized, and there are exponentially decaying functions, and this precisely reproduces the 2-point function on flat space. But I don't know. I mean, the game you're suggesting looks complicated in high dimensions. Also because you have spherical harmonics.
Well, actually, how you do it numerically, you do it slightly differently. You consider first the logarithm of the transfer matrix, and then you know that the energy differences in there are proportional to the inverse correlation length. That is the numerical way which does these things in a much more simple way. You don't have to extract exponential parts from correlation functions. That indeed is very hard.
Okay.
Okay, but nevertheless, we had this discussion about the cylinder, which is very interesting. But the question of Xangu was not about the cylinder; it was about thermal field theory, which is a different geometry. So, can we wrap up? Can you summarize somehow the situation? Because I'm afraid that.
Right. So okay. So going back to that, you can definitely do conformal field theory on finite temperature by compactifying the time. Okay, but then that's a different geometry than cylinder, and they are not related by any simple transformations that I know. So instead, in 2 dimension, if you compactify time, you end up also with the cylinder, but now you exchange time and space, right? Here is different. There have been some work recently trying to relating the beta function of a compact time with beta function on but yeah, I don't think this is a very well explored direction.
No.
So yeah.
I'm surprised, Alessandro, that you are so it has to be said that yeah, so we would like to bootstrap conformal field theories in flat d-dimensional space, but also on other backgrounds. And one interesting background to consider eventually is the background which corresponds to conformal field theory on a thermal circle. So that would be a background R d-1 times a circle.
Yeah, which is different from the cylinder.
Which is, yeah, it's different from a cylinder, but okay, it's in a sense simpler than the cylinder because it's a flat.
Right.
It's a flat.
But this has been done, and there are nice papers on.
Yeah,
this.
that's precisely. I'm surprised because you are not saying that this.
No, I'm okay. No, I'm sorry. I should advertise those papers. There are very nice papers on this. Now, what I was saying is that this is not simply related to the cylinder that we are discussing now, because they're really different geometries. One is R minus D S1, and the other one is R S D minus 1. So that was my answer. Of course, there have been studies at finite temperature, and the problem is you lose interesting features like positivity, because now 1-point functions are non-zero. So there are complications that we will see tomorrow. Perhaps I can make a comment. So you lose a lot of power that we have now, but it can be done. It has been done. There are at least 2-3 papers on it.
Yeah, so we will probably, I'm going to send Xiangu some references to the thermal bootstrap. I also would like to comment on, they're kind of in the discussion mode now. So I would like to comment to Malte about what he was saying about the cylinder in higher dimensions. Because Malte, you are one of the first people who did some numerical simulations of high dimensional CFTs. So on the cylinder, by the cylinder I mean the geometry S d-1 times R, there was actually some recent interest in the lattice QFT community, trying, for example, to ask the following question: can we put the 3-dimensional Ising model on the cylinder? Can we simulate it on the cylinder? So that's not an obvious question to do, because you cannot, you have to somehow discretize the sphere, and there is no obvious way to discretize it. You can so the way, so there was some interesting work, and I can send the references to the interested people. Basically the direction by which they went is that they said, okay, we cannot actually put the Ising model on the cylinder, 3-dimensional Ising model on the cylinder. But we can put phi to the 4th theory on the cylinder because it's weakly coupled in the UV. And we know how to discretize a weakly coupled theory. And then if you want to simulate the Ising model on the cylinder, you have to put the phi to the 4th theory on the cylinder and then tune it to the critical point. And there was some work about doing this, and in fact, this has some advantages for extracting scaling dimensions, similar to the advantages that people doing transfer matrix in 2D know very well. But this, I think there's some potential out there for doing numerical simulations of critical theories in 3D and in higher D, but it has not been fully explored. Okay, any other questions? See, there's a comment from Mikola Scott. Okay, that there exist thermal field theories in D = 4, and the physical value of interest there is the pressure. The analog in statistical physics is the Casimir amplitude. It exists in lower dimensions. One can calculate it, for example, via epsilon expansion. Yeah, that's true. Okay, well, if there are no further questions, then maybe we'll adjourn until tomorrow, 10 a.m.
Okay.
All right. Well, thanks, Alessandro.
Pleasure. See
Yeah.
you tomorrow.
Thank you.
You